Why can a composite part look perfectly fine and still be seriously damaged inside? Here's the short answer. Composites are built in layers, so they don't always fail like a solid chunk of metal. Instead of one obvious crack, the danger often starts between layers, where they can quietly separate. That hidden separation is called delamination. Think of a book. You can bend it, twist it, even dent the cover, and the pages can start sliding apart inside long before you notice anything on the outside. To see why that matters, compare a metal part to a composite part under stress. Metals are usually the same in all directions, and when they're overloaded, they tend to yield and deform in ways you can spot: bending, stretching, necking. They often give you warning. A carbon fiber laminate is different. It's a stack of strong fibers held together by a polymer resin, with each ply oriented in a specific direction. That makes composites incredibly efficient, but also more complex. Their strength depends on how well those layers share load, and how well the resin bonds them together. So what exactly is delamination? Imagine two neighboring plies that should be glued together by resin. Under certain stresses, that bond can start to fail and a thin air gap forms. Once there's a gap, the layers stop acting like one thick plate and start acting like separate thin sheets. That changes everything. Stiffness drops, local bending increases, and damage can spread faster than you'd expect. Delamination usually begins in one of two ways: manufacturing issues or service loads, and often a mix of both. During layup, you can trap air and create voids. You can get wrinkles where a ply folds slightly. You can have resin starvation where there isn't enough resin to fully wet the fibers, or contamination, dust, moisture, oils, that weakens the bond. Even if the outside looks beautiful after curing, tiny defects inside can become the starting point for separation later. Now, composites are amazing at carrying loads in the fiber direction. That's the whole point. But they can be vulnerable to loads that try to pull layers apart. Engineers call these out-of-plane stresses, peel and interlaminar shear. You see them near bolt holes, sharp corners, stiffener runouts, edges, and places where geometry changes abruptly. In those spots, the laminate can behave like a stack of cards, strong in plane, but easier to unzip between plies when the loading is just right. Impact is where composites really mess with your intuition. A small hit, dropped tool, runway debris, a parking lot bump might barely mark the surface. But inside, the shock wave can crack the resin and break the bond between layers. That's why you'll hear the phrase, barely visible impact damage. The part looks fine, but internally, delamination can spread like a bruise under the skin. And delamination doesn't always stay the same size. Under cyclic loading, vibration, repeated bending, pressurization cycles, tiny cracks can link up and the delaminated area can grow. Environment can accelerate it too. Moisture can weaken the resin over time, and temperature cycles can pump stresses into the interfaces because fibers and resin expand differently. The laminate might still pass a quick visual inspection while the internal structure is slowly losing integrity. So what does delamination do to performance? One big effect is buckling. If layers aren't bonded, the laminate locally loses thickness and stiffness. Under compression, that area can buckle earlier, concentrating stress and making failure more likely. Another key concept is compression after impact. A composite panel can survive an impact, but its compressive strength afterward may be dramatically reduced because the internal delamination acts like a built-in defect. That's why composites rely so heavily on inspection methods that look beneath the surface. Ultrasound scanning can map internal separations. Thermography can reveal hidden defects by how heat flows. Even simple tap tests can sometimes detect a change in sound where delamination exists. And on the prevention side, engineers use toughened resins, better layup controls, smooth ply drop-offs, stronger interlayers, and sometimes through-thickness reinforcement like stitching or pins to make delamination harder to start and harder to grow. So the big takeaway is this: composites don't fail differently because they're weaker, they fail differently because they're layered, directional, and often quiet about internal damage. If you judge them like metal, you'll miss the real story happening underneath. Next question for you: where do you think hidden delamination is more dangerous? Aircraft structures, wind turbine blades, or high-performance cars?